Hi, class. I hope you're all doing well. Welcome to the last lecture of the quarter. We have two half lectures, as always, and today we're going to talk about actually traveling to the stars rather than sitting here on Earth and looking outward. Certainly in the back of many people's minds when they imagine life on other worlds or finding life on other worlds or finding extraterrestrial intelligences that we might communicate with. One of the things that's always in our minds are those science fiction visions that we've always generated with books and movies of what it might be like to travel to another world. So what I want to do today is talk about the reality of that. This is covered in the last chapter of the book. So here in the first half of the lecture, we're going to talk about special relativity, which is actually what makes this all possible. Some of you may have been exposed to special relativity before in physics classes if you've taken it. We're just going to touch on a couple of the things about relativity, not certainly everything that we could talk on. And then for the second half of the lecture in the next recording, then we'll actually talk about starship concepts. And then we will be done for the quarter. So I hope you're all doing well. Let's get to it. I'll start with a few slides. Oh, first, let me talk about the background here. So this is a very general background. It's a field of synchronized clocks on posts. Einstein, when he was first thinking about relativity, was entranced by the idea of time. And in particular, he was interested in the idea of how you synchronize clocks and communicate the information between two clocks so that they would read the precise time at the precise moment. There's a really great book called Einstein's Clocks and Poincaré's Maps. It's a public level book about relativity. And in there, they talk about a story about Einstein who was very motivated by his study of the clocks in the train station in Bern and how the synchronization worked. Okay, so that's what the background's all about. Where synchronization of clocks is a huge part of the study of special relativity. If you take special relativity or you take physics from me in the future at some point, and we study special relativity, we'll certainly talk about it then. But today we're going to talk about just a couple of the points of relativity that are relevant to starship travel. Okay, so let's go ahead and do a few slides then, as I was intending to do. Okay, so this is a very famous statue of Einstein. This is in Washington, D.C., outside the National Academy of Sciences. If you ever go visit Washington, D.C., it's not necessarily always on everyone's list. But if you do walk over to the National Academy, it's quite large. As you can see, I sit on Einstein's lap and argue with him about the precepts of relativity. He is unmoved by my arguments. I'm pointing there that top row of equations on there where it says R mu nu equals G mu nu R equals KT mu nu, which you can't see. Those are the founding equations of general relativity, which is Einstein's synchronization of special relativity, which we're talking about today, with gravity. And that leads to black holes and gravitational waves and wormholes and all of those things you may have heard of. So that's what I study. That's what my research specialty is. And so it was really fun to go visit the Einstein statue and pretend I was having a discussion with Big Al. So what are we going to do today? So we'll start by discussing what special relativity is. Many of you have certainly heard about special relativity and heard about some of the odd things that happen in special relativity, or things that seem odd to us in terms of our everyday slow motion lives. We'll talk about what some of those special relativity weirdnesses are, because they are the things that have relevance to starship travel. And then I want to end with this discussion that you always get when you talk about relativity, which is what is real. Okay? So fundamentally, special relativity is the collection of physical laws, the things that we write down to describe the behavior of the universe. And this collection of physical laws are the ones that correctly describe all motion in the universe, what your physics friends call mechanics. Okay, so that's energy, momentum, motion, kinetics, forces, all of that sort of stuff, right? So special relativity is the physical laws that describe motion in the universe at all speeds, including speeds close to the speed of light. And that's really the important part. The laws that you are taught when you take fundamental physics in high school, or if you took it in college, Those are the ones that were discovered and written down by Newton and Galileo, and they are perfectly well suited for life at ordinary speeds, the lives of at the speeds of baseballs and passenger jets and those sorts of things that you and I encounter in our everyday world. They do break down, they don't correctly describe what we see happening when we travel at much higher speeds, in particular as we approach the speed of light, as we can certainly do when we use our particle accelerators, okay? But what is true is if you take special relativity and you look at how it behaves at slow speeds, it correctly gives you Newtonian mechanics, the mechanics that you're taught when you first take physics. And so this is the whole point, is that special relativity is really the appropriate, correct mathematical description of the law of nature. It obeys every experiment that we've ever seen. And when you use it to do slow physics, physics of my and your life, then it still gives you the results that you come to love and learn when you take physics, okay? So what fundamentally does special relativity tell us how to do? It tells us how to measure and define space, that is the things you do with rulers. It tells you how to define and measure time, the sorts of things you do with your wristwatch or these days with your phone, if you're a modern person who has a digital watch, doesn't have a watch but only has your phone. And it also defines how to measure energy. And this is probably the one thing that is the most famous about special relativity. If you talk to just about any person on the planet, if they know any single equation from physics, it's Einstein's famous energy equation about the equivalence of energy and mass, E equals mc squared. That comes from the fundamental study of relativity. Okay? So one of the interesting things about when Einstein first wrote down special relativity, so this was in 1905, it's what we call the miracle year. He wrote 5 really fundamentally transformative papers about modern physics that literally defined the landscape for all of modern physics in the 20th century. And one of those papers was about special relativity. And what we discovered, what Einstein himself discovered after he first wrote down the mathematical description of special relativity, is that it was already built into many of the physical laws that we knew about. We just hadn't realized it. So if you've taken physics, then you probably have studied electricity and magnetism, which are both represented by a set of equations called the Maxwell equations. Well, special relativity is already built into the Maxwell equations. We just didn't know it. Okay, and so Einstein himself was the first person to start investigating this, and what he discovered is that gravity, notably, did not contain special relativity, and so that's what led him down the path of developing general relativity, which you may have also heard of, as we said a moment ago, is the thing we use to talk about gravitational waves and black holes and all of that sort of stuff, and he wrote down general relativity in 1915. Now, this is a picture of the Large Hadron Collider. It is currently the largest, most energetic collider in the world. It's located on the boundary of Switzerland and France at CERN. The Synergy, it's French actually. I don't know what CERN stands for. Sorry, I should know that, and I don't. You can see there in the middle on the platform standing, there's 2 people. So it gives you a sense of the size of the accelerator. It is quite enormous. But in more than a century, with literally billions of experiments competed in particle accelerators, for every particle we've sent around the particle accelerator and watched how it behaves, no data has ever been collected that contradicts special relativity's description of the world. And that is a profound statement. It is literally one of the most well-tested ideas in physics. It is probably the single most, to my estimation, single most trusted idea in physics that we have ever written down. That is not to say we don't look for violations of special relativity. We look all the time. But in a century of looking, we've never found anything that suggested otherwise. So what is special relativity? Let me tell you what it is. We won't write down any equations at all. I'm just going to fundamentally tell you what it is, and then we'll talk about the fundamental effects that we care about. So all of relativity derives from this statement. This is called the postulate of relativity. It's the only thing that you have to assume in order to derive all the results of relativity and use them to go test and do experiments in the world. The postulate itself can be tested. We have certainly tried many times to exceed the speed of light. We have measured whether or not everyone measures the same speed of light, and for every experiment that we've ever done, it seems to be true. So this statement here, that the speed of light is the maximum speed in the universe and that everyone observes it to have the same speed no matter what they're doing, is the fundamental postulate. If you assume that's true, okay, if you start from that premise, then you can explain every experiment we've ever seen. You can explain all the effects that we see happening. And so the kind of fundamental things then that derive from this postulate are the following. If you compare your measurements of space, the things you measure with rulers, and you compare your measurements of time, the things you measure with a wristwatch, to the measurements that anyone else makes, you will have different measurements, different values from your experiment, depending on your relative speed compared to that person. If you're both standing still relative to each other, you get identical results. But if you're moving at all, then there will be slight differences in your measurements, or really big differences if you're moving really fast. Some things can be measured that everyone absolutely agrees on, no matter what your state of motion is. Okay, so the speed of light is the first one of those things, but there are other things as well, like energy, total energy. And so such quantities are what we call invariants in physics. And so invariants are really important because they're the ways that we can compare and contrast our experiments to see whether or not we've done them correctly or not, okay? And then lastly, something you've probably heard about, and we'll talk about here in just a minute, is what we call paradoxes, or what are euphemistically called paradoxes. What I like to advocate with all of my students when I teach them special relativity is that there are no paradoxes. Paradoxes suggest that there is no explanation for the observations that you've made of the universe. And in that sense, there are no paradoxes in special relativity. There are things that violate your common sense based on your experience walking around the world at the speed a Yugo can drive, okay? But there's no observations that we cannot explain using the fundamental description of special relativity, okay? Everyone agrees on the ultimate outcome of experiments, although they may not agree on the sequence of events or the sequence of measurements that lead to the outcome of that experiment. Okay, and so that's the sense in which we mean there are no paradoxes. And we'll come back to a couple of the famous ones and talk about them in that context. Okay, so let me tell you about the kind of two fundamental special relativity effects that you may have heard about. They're the ones that are relevant to our discussion today. So the first is something called length contraction. Fundamentally, length contraction says that moving objects are measured to be shorter when they're in motion than when they are at rest. Okay, so imagine you're standing there with a ruler, and you and I are standing there. We're standing still. The ruler is standing still next to us, and we measure the length of the ruler. We'll get some length. I have a ruler here on my desk. It's 30 centimeters long. Okay, if that ruler is in motion, that is moving towards you, special relativity says that the measurement you make of that ruler while it is in motion is shorter than the length you got when it was at rest. And that means whether it's moving towards you or it's moving away from you, okay? No matter which direction it's moving, you will see its length contracted, okay? And the amount of contraction, how much it's shortened, depends on how fast it's moving, okay? Now, that statement is true whether it's the ruler moving or whether it's you moving. If you're moving at some speed relative to the ruler and you try and measure the length of the ruler, then the ruler is still going to be foreshortened. It's going to be contracted, okay? And this is why the special relativity is called relativity. It's not about which object is moving. It's about what's the relative motion between the two. So if there's any motion between you and the ruler at all, you will measure the ruler's length contracted. Okay, and I should say, I wasn't clear here in these slides, that's for motion parallel to the direction of the length of the ruler. Okay, in directions that are perpendicular to the motion, you don't see the contraction at all. Okay, the second weird effect is called time dilation. Time dilation says that moving clocks, and here I'll emphasize all clocks, and I'll talk about what I mean by that in a minute. Moving clocks tick slower when they're in motion than when they're at rest. Okay, so what do I mean by that? Imagine you're standing there and you have two sets of clocks, the red set of clocks and the blue set of clocks. And just like these clocks behind me in the backdrop today, you have synchronized those clocks, okay? So what I'm doing is I'm showing the clocks at 2 periods in time. So the first clock, the one on the left, says it's 1 o'clock. And then the second clock means a half hour has elapsed and it says 1:30. Okay, so I've synchronized the two clocks. They're both exactly 1 o'clock at the same time, and a half hour later, they're both exactly 1:30 at the same time. Okay, now what special relativity says is that if I set the blue clocks in motion, they will tick slower than the red clocks. So that when the red clock reaches 1:30, then the blue clock won't quite be to 1:30. It'll only be at 1:18. Okay, and again, that depends on how fast the clocks are moving. If they're moving around at the speed that you guys drive, then they both stay synchronized to your ability to measure. But if they're moving around at half the speed of light, you definitely know the difference. Okay, now up there at the top, I said all clocks. And what I mean by that is anything that keeps time. You and I are used to mechanical clocks, things that have mechanical motions, gears and levers and springs and pulleys that make the clock hands move. We're also used to digital clocks, things that use oscillating quartz crystals and electrons pushing around them to tick off. But anything that keeps time on a regular interval, like a heartbeat, constitutes a clock as far as relativity is concerned. So you can imagine that if you and I are standing there together and we measure our synchronized heartbeats, and since we're all being very good about exercising while we're in quarantine, right? We have healthy, regular, low heartbeats, right? Bump, 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 in synchronicity with each other. But if one of us begins to move, then special relativity says that your clock ticks slower. And so if I'm standing still and my heart is still going bump, 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 and I look and I compare my heartbeat to your heartbeat, you're moving relative to me, and I see that your heartbeat is going slower. Bump, bump. Okay? You, looking back at me, observe the exact same thing. You think I'm the one moving. And so in that case, you think your heartbeat's ticking at normal rate. Bump, bump, bump. But when you look at my heart, you think it's going slow. Bump, bump. Okay? And that's the weirdness of special relativity. All clocks, if they're moving, tick slower than they do when they're at rest. Okay? Now, when we say that, we're talking about the comparison between something in motion, a ruler, a clock, whatever it is, to something at rest. It's the comparison where the word slower or shorter makes a difference. Okay? Okay, so how do we use this? So let's talk about one of the very first mysteries that was solved with special relativity. And that mystery is called the paradox of the muons. So our atmosphere is constantly being bombarded from outer space by cosmic rays. We've talked about that. The cosmic rays come into the Earth's atmosphere, they hit a molecule, and they generate a shower of subatomic particles, one of which is called the muon. So the muon is an unstable subatomic particle. It only has a lifetime of about 2 microseconds. That means from the moment it's created, it only survives about 2 microseconds before it dies and decays into something else, okay? Now, when they're created about 5 kilometers up in the sky, and they're traveling about 0.995 times the speed of light, okay? And so if you take that 2 microseconds and you count 0.995 times the speed of light, that means a muon, from the moment it's born to the moment it dies, should only travel about 657 meters. But if I build a muon detector in my backyard, you and I can do this, Okay, you can build what are called cloud chambers and detect cosmic rays yourself. Okay, if I build a muon detector in my backyard, I detect muons at a depth in the atmosphere of 5 kilometers when they all should have died 657 meters after the moment they were created. How do the muons get all the way down to me before they die? Okay, this was a great mystery. Okay, well, the answer is special relativity. Okay, so how do you explain it? Well, the muons watch that it's carrying along, the watch it's paying attention to decide when it should decay is ticking too slow. The muon's watching its watch, and it says, I'm supposed to decay after 2 microseconds. But compared to my watch on the ground, its ticks are going very, very slow. And so it reaches the ground before 2 microseconds have passed on its watch. Special relativity tells me the muon's personal clock is dilated, and that's why it survives. The other way to look at the problem is to ask what the muon sees when it looks at the ground. It looks down at the ground, I think it's 5 kilometers away, but the muon sees it contracted. And so the ground is much closer than 657 meters because it doesn't think it's 5 kilometers away. Okay? So special relativity can solve this problem from either viewpoint. And this is really the point. Relativity is self-consistent. Everyone agrees on the outcome of the experiment. We both agree, the muon and me agree that it makes it to the ground. What we disagree on is why. The muon thinks the ground is close, and me watching the muon's clock, I think the muon's clock is ticking too slow. Okay? Everyone agrees on the outcome. We made it to the ground, but the reason is different. Okay? So that's really the whole point in the way special relativity works. Let's talk about another, probably the most famous paradox in relativity. So this is called the twin paradox, okay? So imagine 2 people who are exactly the same age, twins if you will, okay? One of the twins is going to get in a rocket ship and travel away from the Earth at very high speeds, okay? Close to the speed of light. They'll go cruising around the solar system, out into the galaxy, near stars, whatever. They'll turn around and they'll come back, okay? And when they return, what they discover is that they've hardly aged at all, but their twin, who was exactly the same age as them when they left, has now become old and gray, okay? They have aged much, much more than they did when they traveled on the rocket ship. Why? Because special relativity predicts if you travel on a rocket ship at high speed, your clock ticks slower than the people who aren't traveling. So what does that mean? That means when 10 seconds pass by on my clock on Earth, not even 1 second has passed by on my clock on the ship. When 90 years has passed by on my clock on the Earth, on the ship, maybe only 1 year has passed by. You do not age as fast as those left behind. And this will be the important part that we want to discuss, that we want to use when we talk about starship travel, okay? So for a twin on a moving rocket, their clock ticks slower, they arrive back, still a young person, while their twin is old, okay? And that's how we're gonna be able to explore the cosmos, okay? Now, what is the most common question I get about all of this, okay? Every time I teach relativity, the question you get is this: does the ruler really get shorter? Does the clock really tick slower? What really happens, okay? And the answer to that, I think Morpheus in the Matrix expressed the most clearest I've ever heard it expressed, okay? What Morpheus said was the following.
What is real? How do you define real?
What is real? How do you define real? Okay, now you and I are scientists, right? And when we talk about what's real, what we're talking about is what happens when I do an experiment, when I make a measurement of the nature of the world. And what we regard as real is the data at hand. And so if I measure the length of a moving ruler, I measure it to be shorter. That is the real statement. If I compare my clock at rest to a clock that I see traveling by at half the speed of light, I observe the clock going by to tick slower. That is real. It really happens because I'm using the laws of physics to understand my measurement, and relativity tells me how to compare the measurements of my ruler at rest to a ruler moving at half the speed of light. Special relativity tells me how to compare the ticking of my wristwatch to a wristwatch traveling by at 0.9 the speed of light. The measurements that I observe are what we define to be real. Okay? In a similar vein, those rulers flying by and those clocks flying by make measurements of my clock and my ruler, and they don't see the same values that they see of the clocks and rulers they're carrying with them. It's really real. It really happens because that's what observations mean. Okay? Okay, so there's lots more, obviously, that we could talk about with special relativity. There's lots more brain-melting stuff. There are lots of good public-level books about relativity. I probably should have put some here in the talk. I'm sorry about that. I normally remember to do that. I forgot. But if you ever take general physics, you will study this a little bit more. And if you're interested, please don't hesitate to reach out. I can certainly point you to some resources to learn some more. But this is what we're going to use. We're going to talk about these precepts of time dilation and use them in our study of starships next. Okay? So I hope you're all well. Stay safe, and I'll talk to you again in a little bit. Take care.